Hi class. In this video we're going to go through the variation of parameter solution technique for non-homogeneous linear constant coefficient differential equations. So I'm just going to do a few exercises out of your homework. We're going to start with number 2, which reads 2y prime minus y equals e to the x. What we want to do first in all of these, for all non-homogeneous problems, is to actually solve the homogeneous problem first. To do that, we write the auxiliary equation, which in this case is 2m minus 1 equals 0, which leads to m equals 1/2. And I write down the homogeneous solution. Since this is first order, it's just going to be c e to the 1/2 x. There's no need for a c2. Okay, well, half of my problem is already done. The second part is figuring out the particular solution, which I'm going to call yp, p for particular. And the idea is that we say it should be u times y1, where y1 is the homogeneous solution with c set to be 1. So if you read back through the chapter, you'll find that there's actually a formula for this u. We get u prime is g over a y1. G is the quote-unquote the thing that's making it non-homogeneous. So we fill in this formula, and then we're going to have to integrate. So let's see. G is e to the x. A in this case is 2. A is the coefficient of y prime, it's of the highest derivative term. And y1 is just e to the 1/2 x. 1/2 x, sorry. And now we need to simplify this as much as possible because it shows up later in our solution. Okay, so let's see, that's 1/2 e to the x over e to the 1/2 x is e to the 1/2 x. So u is the integral of 1/2 e to the 1/2 x dx, which is just e to the 1/2 x plus c. Now, it turns out that any antiderivative will work. Now, we want to make this thing as simple as possible, so we're just going to set c equal to 0 in our formula for yp. Well, let's see, so y1 was e to the 1/2 x. E to the 1/2 x times e to the 1/2 x is e to the x. So my particular solution is just e to the x. How do I get the overall solution? Well, that's easy. Because it's linear, we can add these two solutions together. And so I'm just going to write yp plus yh, and I'm going to mark where you can find yh and yp. That's all there is to it. Okay, so let's try a second one, which is a little bit more involved on the integration side. So what I found through teaching this course several times is that usually this procedure is clear. It's the integration from Calc 2 that trips students up. So if you're worried about that, maybe you should check out the appendix and do some practice intervals. Okay, so here we have y prime minus y equals 1 plus e to the 2x all to the negative 1. We start out with the auxiliary equation, which is just m minus 1 equals 0. So m equals 1, which tells us that the homogeneous solution is c e to the x. Once again, it's not second order or third order or anything like that. It's first order, so we just need c e to the x. It's not a repeated root or anything. Okay, moving forward, we have yp equals u y1. So I guess I should say that y1 is just e to the x. And u prime is g over a y1, which is, oh no, this looks really complicated. It's 1 over e to the x times 1 plus e to the 2x. And so the main difficulty in this problem is figuring out how to integrate 1 over e to the x times 1 plus e to the 2x. If you stare at this a little bit, it looks suspiciously like partial fractions. And in fact, it is partial fractions, except we need to make a change of variables in our integral first. So, what letter should I use? Let me make a v substitution and write v equals e to the x. Then dv should be e to the x dx. And I can kind of see that I'm in trouble. I can't make this substitution because I don't have e to the x dx. Fortunately, what I can do is multiply the top and the bottom by e to the x. If I do that, I'm left with e to the x over e to the 2x times 1 plus e to the 2x on the bottom. Now I can make my substitution, and I get u equals the integral of dv over v squared times 1 plus v squared. Now it's just a partial fractions problem. 1 over v squared times 1 plus v squared is av plus b over v squared plus cv plus d over 1 plus v squared. So that leaves me with 1 equals, and if I just cross multiply here, I'll get av cubed plus bv squared, excuse me, plus av plus b plus cv cubed plus dv squared. Collecting terms of this polynomial tells me that 1 equals a plus c b cubed plus b plus d b squared plus av, and I'll put that in parentheses for no real reason, plus b. And thus I get a system of 4 equations with 4 unknowns by equating the coefficients of v cubed, v squared, v, and the constant term on the left and the right. So let's see, v cubed, v squared, v, constants. On the left, they're easy. Only the constant shows up on the left. On the right, we get a plus c, b plus d, a, b. And at first, it looks like this is going to be a pretty hard system to solve, but a few of them jump out immediately. In particular, a and b are easy to solve from these two equations. A must be 0, and b is 1. If a is 0 and I plug that in here, that tells us that c is 0. If b is 1 and I plug that in here, d is negative 1. So this tells me that this integral is the integral of, let's see, 1 over v squared minus 1 over v squared plus 1. So that u is negative 1 over v minus arctan of v. Again, plus c, but I don't need the, I'm going to set c equal to 0 to make my life easier. So the particular solution is 1 over v, negative 1 over v, but v is e to the x. So negative 1 over e to the x minus arctan e to the x, all times y1, which is e to the x. I can simplify this and get negative 1 minus arctan e to the x times e to the x. That's my particular solution. My homogeneous solution is here. So ultimately, the solution is y equals the particular solution plus the homogeneous solution. And that's it.